You are standing in a city at night. Look up. That star you see. The one that's been there for your whole life. Reliable, distant, eternal. It is already dead. It died before your great-grandmother was born. The light just arrived now. And when it lived, it was young and thoughtless and burning itself away without knowing it would ever end. Stars don't last forever. This is something we know. This is something we accept the way we accept that our own bodies will one day stop. But knowing something and understanding it are different things. And what happens when a star much larger than our sun reaches the end? What happens in those final moments is so violent, so dense, so utterly wrong that physicists had to invent new rules of the universe just to explain it. A few times every second, somewhere in the observable universe, a massive star is dying, not dimming, not fading, collapsing, imploding inward with such force that the atoms themselves cannot survive. The electrons are crushed into the protons. The distinction between things stops existing. What remains behind is something so dense, so compact, so fundamentally broken that a teaspoon of it would weigh as much as all the cars in the world combined. This is called a neutron star. And it is not a quiet death. Not at all. The star that creates a neutron star spends most of its life doing the same thing ours does. Burning hydrogen into helium, pushing outward with the heat of fusion, being held back only by its own crushing gravity. It is a balance. For millions of years, this star holds itself together in this dance between explosion and implosion. But massive stars are wasteful. They burn through their fuel faster. And when they run out, there is no slow fade. There is only collapse. When the core finally runs out of nuclear fuel, there is nothing left to hold it up. Not even a moment of warning. The weight of the entire star, tens of times the mass of our sun, comes down on itself all at once. The gravity does not ask permission. It does not negotiate. In less than a second, the core crushes inward. Electrons are forced into protons. Protons become neutrons. The electrons and protons no longer exist as separate things. Reality is being rewritten in real time. But gravity does not get to keep going forever. At some point, when the neutrons are packed so tightly that they are almost touching each other, they push back. They have no more room, no more space to compress into. The inward collapse suddenly reverses. It rebounds with such violence that it creates a shockwave, an explosion so powerful that it blows the entire outer layers of the star away into space at speeds of 30,000 kilometers per second. We call this a supernova. And what is left behind, in the center of all that violence, is the corpse. The corpse is still burning, not with fire, with radiation, with the heat left over from its own violent creation. It spins. Sometimes, many times per second. It has a magnetic field so strong that it would erase the data on every hard drive on Earth if you brought it within the distance of the moon. It is a lighthouse made of crushed matter, spinning in the dark, broadcasting radio waves across the galaxy. This corpse is what we call a pulsar. This corpse is a neutron star. And here is the thing that makes you need to keep watching. There is something we still do not fully understand about them. Something about the way they shine. Something about where their energy comes from. The physics that we built to explain the universe does not quite work when it comes to neutron stars. They force us to admit that we have not finished learning, that the universe is still stranger than we thought, that there are still mysteries in the corpse of a dead star. To understand what a neutron star is, you have to understand how wrong it is. And to feel that wrongness, you have to start with something you can hold in your mind. Imagine a sugar cube. That is a small, familiar object. You can picture it easily. Now imagine that you were to take all the matter from a neutron star, all of it, and compress it into the shape of a sugar cube. How much would it weigh? The answer is roughly 900 billion kilograms. That is the weight of Mount Everest. Take Mount Everest, the tallest mountain on Earth, and pack it into something so small you could hold it in your hand, and you would not be able to move your hand. Your hand would break. Your arm would break. Your entire skeleton would collapse under the weight. But before any of that happened, the gravity from that sugar cube would pull you toward it with such force that your body would be torn apart atom by atom as you fell into it. But this is still just a number. Numbers are not real until you feel them. So imagine a different scenario. Imagine that a neutron star the size of New York City has somehow ended up in the solar system. Just sitting there, between Earth and the Sunday. The gravity from this thing would not just pull you toward it. It would pull on every atom in your body differently. Your feet would feel 10 billion times more gravity than your head. The difference would stretch you. Not quickly, not gently, but with absolute certainty. The neutron star would turn you into spaghetti. We call this spaghettification. It is not a fast process if you fall in slowly. You would live long enough to notice what was happening. You would feel your feet being pulled away from your body while you fell. This is not theoretical. This is what neutron star gravity does. This is physics. The actual size of a neutron star is staggering. Most of them are between 20 and 30 kilometers in diameter. That is the width of a small city. Take all the mass of our sun, 2,000 billion kilograms of it, and compress it into a sphere that wide. The result is a neutron star. Our sun is so large that light takes 8 minutes to travel from its surface to Earth. A neutron star that contains more mass than our sun is small enough to fit inside the orbit of the moon. Think about that for a moment. Let it sit with you. More mass than everything we can see in the sky, compressed into something smaller than the place where we put our satellites. But the neutron star is not just there, sitting silently. It is spinning. When the original star collapsed and formed the neutron star, it was already spinning slowly the way all stars spin. But as the matter compressed inward, the spin got faster. This is the same reason an ice skater spins faster when they pull in their arms. Except the neutron star does not have arms, and it does not slow down and speed up. It just keeps spinning, faster and faster. Some neutron stars spin once per second. Others spin 30 times per second. The fastest ones we have ever found spin 716 times per second. Imagine a city-sized ball of matter that is heavier than the sun, spinning 716 times every single second. The surface of such a neutron star would be moving at a significant fraction of the speed of light. The relativistic effects, the strange distortions of space-time, would be extreme enough that we need Einstein's equations just to describe what is happening. And all of this is happening in the dark, in the middle of space, billions of kilometers away from anything else. But neutron stars do not just spin. They send out signals. They have magnetic fields so powerful that they create beams of radiation that sweep across space like a lighthouse beam. When we point our telescopes at them, we see pulses of radio waves arriving at perfectly regular intervals. This is why we call them pulsars. For decades, when astronomers first started detecting these signals, they thought they might be aliens trying to contact us. The signals were so regular, so artificial seeming, that it seemed impossible they could come from nature. They were wrong, but only slightly. The signals do come from nature, but from a process so extreme that it might as well be magic. When matter falls into the magnetic field of a spinning neutron star, it does not land gently. The magnetic field rips it into pieces. It accelerates charged particles to nearly the speed of light. These particles emit radiation. A beam of radiation, concentrated and focused by the magnetic field, shoots out from the magnetic poles. And because the neutron star is spinning, this beam sweeps across space like the light from a lighthouse. Every time the beam points toward us, we see a pulse. Every time it points away, we see nothing. The pulses are so regular that some of them keep better time than atomic clocks on Earth. There is a neutron star, right now, somewhere in the galaxy, that has been ticking with the same rhythm for billions of years. It will keep ticking long after the sun has died, long after the Earth has turned to ash, long after the last star in the universe has burned itself out. The universe is a dark place, but there will be neutron stars still spinning, still pulsing, still burning with the radiation of matter falling into their gravity. And here is what we still do not fully understand. Some of these neutron stars should have slowed down by now. They should have lost energy over billions of years and now be spinning slowly, like ancient clocks winding down. But some of them are spinning faster than they should be. Impossibly faster. We see evidence of matter being pulled off companion stars and spiraling into the neutron star, which would speed it up. But the acceleration we measure is still too fast. The equations do not work perfectly. The universe is still holding secrets about how neutron stars work. Some of these spinning neutron stars, called millisecond pulsars, are in binary systems with other stars. Matter spills from the companion star, spiraling inward, burning as it falls. These systems create some of the brightest X-ray sources in the sky. The radiation comes from matter that is being heated to tens of millions of degrees hotter than the core of the sun just from the friction of falling into a gravity well. The energy output is staggering. One of these systems can outshine millions of regular stars, all from a process happening on the surface of something smaller than New York City. The universe is not finished revealing itself to us. And in the presence of a neutron star, human physics feels young and uncertain. Let's zoom all the way back out now. Let's remember where we started. You are standing on Earth. You are solid. You are made of atoms that feel like they are hard and real. You feel heavy. You feel permanent. And yet every atom in your body was created in the furnace of a star. Some of them were created in the furnace of a massive star, the kind that ends as a neutron star. Those atoms lived through the collapse. They were there in the final moments before the core imploded. They survived the supernova. They were scattered into space. And eventually, they became part of you. This is not poetic language. This is physics. This is chemistry. This is fact. The iron in your blood was cooked in a star. The calcium in your bones was created at the moment when a massive star was dying. You are not metaphorically made of star stuff. You are literally made of it. You are an arrangement of atoms that were, at one point, in the center of a stellar furnace. And now consider this. Somewhere, in the Milky Way galaxy, there are thousands of neutron stars. Some of them are young and still cooling from their creation. Some of them are billions of years old. They are all pulling matter from their surroundings. They are all slowly building up a thin layer of new material on their surfaces. And they are all, eventually, going to die. When a neutron star finally exhausts the matter it is pulling from its companion star, it will go dark. It will still be there. It will still be spinning. But it will no longer emit light or radio waves. It will become a black widow, a dead thing that keeps no light of its own. In the end, even the corpse of a star loses its fire. But this is not the end of the story. Far from it. Because what happens after the neutron star goes dark is that it will eventually become something else entirely. If a neutron star collides with another neutron star, they will merge. The collision will create the heaviest elements known to exist: gold, platinum, uranium. These elements will be scattered across space in the explosion. And inside the merger, where the pressure and temperature reach extremes that make even the heart of a neutron star look gentle, something new will form: a black hole. A black hole is what happens when gravity wins completely. When there is no force left in the universe that can hold back the inward crush of space-time itself. A black hole is a wound in reality, and it is made partly from the corpses of stars. The universe recycles. It takes the ashes of dead stars, combines them, crushes them further, and creates something so extreme that light itself cannot escape. And we still do not fully understand black holes, either. We know they exist. We have seen their shadows. We have measured their effects on the stars and matter around them. But the physics at the center of a black hole, where the laws of physics as we understand them break down completely, is still a mystery. The universe is still keeping secrets. So what does this mean for us? What does any of this matter? Here is what matters. The universe is far stranger and more extreme than the everyday experience of human life suggests. We live in a bubble of comfortable gravity. We live on a planet where the rocks do not crush us, where the fire does not consume us instantly, where atoms maintain their integrity and allow complicated things like bodies and minds to exist. We take this for granted. We think this is what the universe is normally like. But normal is rare. Normal is the exception. Everywhere else in the universe, things are being crushed and burned and torn apart. Everywhere else, matter is being subjected to forces so extreme that the normal rules do not apply. And yet, from these extreme places, the building blocks of life are created. Without neutron stars, we would not have the heavy elements needed for planets and bodies and brains. The universe that created us is the same universe that can crush matter into a density so extreme that a teaspoon weighs as much as a mountain. The universe that gave us life is the same universe that creates wounds in space-time called black holes. We are made from the violence. We are made from the extremes. We are arrangements of atoms that have experienced conditions so intense that they should not exist. And yet, they do. And that means we should be grateful. Not because the universe is kind. The universe is not kind. The universe does not care about us. It does not know we exist. It would crush us as easily as we crush an insect, without malice and without hesitation. But the universe, in its indifference, has created something that can look back, something that can point a telescope at a neutron star and measure its spin to a fraction of a second, something that can understand the physics of gravitational collapse and stellar death, something that can hold in its mind the weight of a mountain compressed into a teaspoon and feel the strangeness of it and be moved by it. We are that something, and we are made from the corpses of stars. The universe is still burning. It is burning in 10,000 neutron stars right now. It is burning in the cores of living stars, slowly building the elements that will one day become part of someone's body, someone's mind, someone's moment of understanding that they are made from the violence of creation. The neutron star you are thinking about right now, the one we discussed, the one spinning in the dark, it is still there. It is still pulsing. It is still burning with radiation. And it will keep doing these things for billions and billions of years after you are gone. After everyone you have ever loved is gone. After the human species is gone. After the sun has expanded and boiled away every ocean on Earth. The corpse is still burning. And somewhere in all of that burning, in all of that violence and heat and radiation and gravity so extreme that it breaks the normal rules of the universe, there is beauty. Not the beauty of a painting or a song, but the beauty of something true and real and strange beyond anything we can fully understand. The beauty of the universe revealing itself slowly, fact by fact, mystery by mystery, to the small arrangements of atoms that manage to think about it. That is enough. That has to be enough. Because the corpse is still burning, and we are here to watch it burn.